Hi, and welcome to the ZP Developer Zone and the ZP Developer Zone webinar specifically. And we do this webinar every Thursday at 8 a.m. London time. Now, it's not actually 8 a.m. London time. It's something like 56 minutes past midnight on Thursday, the 25th of May. Now, the reason this is happening is some of us are on a trip at the moment. We've actually been giving a talk at MIT, the Massachusetts Institute of Technology, and we've also been on a tour of the facility. So it's a little bit confusing, but we'll be on flights tomorrow at the normal time. So we've actually come and started this early. But let me kind of jump into it a little bit and just say, we do put this slide up every week, and really it just talks a little bit about, that we do have the ZP Academy. If you have sort of general questions around electrochemistry, don't hesitate to, use the ZP Academy, if I could put it that way. And also, we do the webinar. If somebody has a technical question, we try to kind of support during the week. Collaborations are, strictly speaking, running at the moment, mostly in Norway and the UK, where there's really funding for this. We do offer jobs. Somebody's asking us for a PhD position at the moment, and I am actually just saying, look, with regards to that, we do have them at the CDT in Glasgow, and we do have them also being advertised with Swansea University. There is the ZP Developer Zone, and there's also the workshops, and I'll touch upon the workshops a few times. So as I say, it's very early in the morning in the UK, but actually that's because we're on the East Coast, so we're in different time zones, and it's the MIT trip that has confused things a little bit. We will be having our workshops as normal in June, so there will be one in the UK and one in Norway, and this covers all matters to do with electrochemistry and electrochemical biosensing in particular. If you see a link, I've already put the links underneath the video, so these links will, if you see a link and it's relevant to a particular slide, you'll be able to find those underneath the video. The first one tonight is about changing the connector on a flow adapter. I will touch upon that. And another question tonight is about using a PEC2 cell. I will touch upon that. The other one's about doing a sensor for phenol. I put here / catechol. Catechol is just a diphenol, basically. And there's also been a question about Sarissa Biomedical and the sensors from Sarissa Biomedical. This was a company that went into distress. I get a little bit confused tonight, but it may be a couple of years ago when ZP took over the assets and took over the building and took over the team. There's also a question around ecFLEX. This has been going for a few weeks. And then a question about measuring calcium and magnesium. We do have a calcium sensor. I will touch upon that. And then how to, graphene electrodes and how to functionalize those graphene electrodes. And I also recommend some potentiostats as well. Somebody was, they've ordered a flow cell and they would like a wiring diagram for the cable. And we can't give a wiring diagram because a wiring diagram will sort of say that we're officially suggesting that this person actually modifies the cable. And we're a bit worried about, we're not so worried about them damaging what we give them, we're just worried about them damaging the potentiostat that they have. So I'll give you a bit of a backstory on this, and I'll also tell you that in the past we have given out wiring diagrams. So it's not that we're against wiring diagrams, it's just we are now, because actually we've done it in the past and it slightly backfired and somebody sort of damaged their equipment, and it wasn't, to be frank, it wasn't our fault. But I'll touch upon that anyway in the next few things. So if you're ever ordering a flow cell from us, you'll actually find that our production team will reach out to you and ask you what adapter do you want. And in this case, we reached out and we asked for they told us they wanted an LM5, which in our world is a LEMO 5 connector. They come in LM4, and they also come in this kind of much more generic banana plug connector. Now, my guess is in this case, they probably needed a much more generic banana plug connector. Now, what's important to note here is that even if these cables are shielded, when we're giving it in the banana plug configuration, we're not actually using, the shielding is in place, but the shielding is not being connected to the ground. So what it says to you is that the ground usage of this cable is not critical, because we sell it in a version where even though we leave the shielding in place, it's not being clipped to ground, so it's not really doing anything. Now, the reason I say this is I can't give you an official wiring diagram, because then I will be officially sanctioning that you can modify this cable and you can use it in your potentiostat. I can't do that officially. I'm going to open myself up to liability. I will give you a personal opinion, which is I would just cut the cable and solder on my own banana plugs, but that is on you, and that's not something that we can sort of officially recommend. The reason this is happening is because actually we will support our own potentiostat. So we have the AnaPot. So if anyone's interested in doing electrochemical research, it just happens to have LM4, the LEMO connector 4 on the back side of it. The AnaPot is good for DC techniques, so that's everything bar AC techniques, which is impedance spectroscopy. So AnaPot has a LEMO 4, the AnaPot EIS has LEMO 5, and if you look at the back of it, you can see the LEMO 5. So that's why there's this confusion on cables, but we always check before we ship them, and in this case, we did actually check it. I've put some links to those potentiostats, and those links to potentiostats are useful because we have had some inquiries this week, which is how do I get started with electrochemistry? Where do I start? Well, these are probably the electrodes that you should start with. Like I say, it's not that we, in the past, we have actually given out wiring diagrams. I show it here. This is for the LEMO 4, but it's not for the LEMO 5. So we've done this on our website, but unfortunately, it did sort of mean that somebody misinterpreted the wiring diagram and went in a direction I wasn't particularly happy with. So in this case, we've offered to actually fix their problem, but unfortunately, it's a custom cable. In this case, if you want to avoid the costs, I would refer to my earlier slides when I said, we do it in a banana plug flavor. And so you could actually just adapt your own cable, but unfortunately, the risk in this case is upon you. If you want the risk to be upon us, then it will have to go the more official route, and that's a custom cable, customized cable LM5, which we can do. But I completely understand that you want to avoid the cost, but of course, by the time our engineers have looked into it, etc., it does get expensive to do this kind of customization. So, but I did want to demonstrate to you it's not that we don't want to help; it's just we have in the past, and it's backfired on us. Another question I had in here is somebody asked us about a PEC2 cell a few weeks ago. They ended up getting one, but from somebody else. But we're good people, so we will support. The problem they've got is with this PEC2 cell is that they showing us an image here where they're pushing liquid into it and the liquid's popping straight out again. I find it a little bit curious because I can see the kind of water level, so the water level is not so high. I think there's literally just some liquid has got inside this joint, inside here. So what happens is when they push down here, there's just a bit of liquid in here and it just pops straight out again. Because I can obviously see that you have liquid in there. So I don't think this is a serious problem, but how I fix it is I'd actually, there's some liquids got trapped in here. I'd actually suck it out with a bit of tubing and a syringe, just suck out that liquid. And then you should be able to just sort of pipette back in. But I can see that your liquid level is not so high because I can see your liquid level there. So I hope you're able to just suck out whatever liquid is in there. But I mean, in this case, this was purchased from another company. So I think, unfortunately, you do have to kind of go to them and get their technical support. If it was with us, then we would obviously be very keen to support you. I'm going pretty quick because for me, this webinar is advertised to go out at like 8 a.m. London time. Well, it's something like I'm very confused actually. It's actually about 1:05 in the morning London time, so we're a bit jet lagged. But let me go a bit quicker and talk about detecting phenols. Somebody's thinking about making a sensor for phenols using liganolytic enzymes, and I had a quick look at these enzymes as lacase, lignyl peroxidases, magnesium peroxidases, versatile peroxidases. So I did originally suggest that they were actually going to use some of our platinum electrodes. I had good rationale for this, and this is really part of our workshops that we do every month, and that they would take one of our platinum electrodes, they would immobilize the enzyme on top, they may put a barrier layer on top of that, their catechol or their phenol would come in, it would react with the enzyme, it would generate, when reacting with the enzyme, it would generate to form hydrogen peroxide. The hydrogen peroxide would diffuse to the electrode, and if you apply a voltage, you get a signal. This is very classic, and people who have seen this webinar before from us will recognize this is pretty much how you make what's called a generation 1 glucose sensor. So I in an email I suggested to them, oh yeah, we'll just get some hypervalue platinum electrodes, which I've put a link to in the way as well. It's worth saying that if you are getting into electrochemistry or electrochemical biosensing, these are super good electrodes to get. The sheet here, which has about 300 on there, has cost about €500, so it's €1 and a bit, sort of approximately €1 45 cents each for a electrode. But I had a look at the literature a little bit closer, and I realized that at least this lacase enzyme, it reacts with oxygen the way I was showing in my mechanism, but it goes all the way to water. So water is not, electrochemically active. So in fact, don't do what I just suggested, because according to this literature, it's not going to work. But at ZP, we will take the effort. I've put some links in here, so hopefully this will help you. I did take the effort and have a sort of slightly deeper look in it. And I did find some literature references for this again. And in fact, it was a Nature paper as well, made me think, this is probably quite a sound paper, and I would actually try it. And I think it was a bit more of a benefit, actually, because there they were using, I'm pretty sure it was a carbon electrode. They might be modifying it with graphene, but I call it current collector, or their electrode in this case was a carbon electrode, which is good news because these are even, whoops-a-daisy, sorry, I saw an extra link there. Yeah, I linked to the carbon electrodes. These are super low cost. You risk very little. And actually try this paper to make your phenol sensor. Obviously, I'd love it if you've got our potential stats. You definitely want our electrodes, and then it will help you because we're probably more likely to support through the webinars. We did get an inquiry that somebody from 2019 has got some electrodes that were from a company called Sarissa. Sarissa went into liquidation, but luckily ZP came in and bought all the assets. And I just want to, their question was, do we still make these products? Good news is, yes, we do make these products. And I've put a link to the website. And I also want to say that we will be having a workshop on biosensors for neurosciences. And I've hopefully put a link underneath the video, but they will be happening in September 2023 in conjunction with the University of Warwick. There we are, and I've put another link to that here. These workshops are really good, actually. I mean, they're super practical. We have one on screen-printed electrodes, we have one on electrochemistry, we have one on neurosciences, or biosensors for neurosciences. Everyone gets to make electrodes, everyone gets to take home electrodes. This is not, sit there and be bored by a lecture. And there's also a lot of, tricks and tips and a lot of commercial insight as well from ZP, because, we are extremely technical, but we also are, quite commercially astute, and we understand the commercial landscape, let's say. So if somebody's a user of our products, we will support them. This is an example of an ecFLEX problem that somebody's having at the moment. We've taken a look at it. First of all, we realized that they weren't, they were trying to do some testing with just resistors. So we advised them that they need to complete the circuit. So that we did sort of advise them on that. And there was a video I put out. So the video is about potentiostats, which I also shared with them. So they went away and did what we advised. That's great. And sent us a few videos of showing us what the resistances were, so that's all working fine, but it still wasn't working, which is, now I shared this with an engineer and we had a little bit of a chat about it. Now at ZP, as you would expect with something like the ecFLEX, we actually did test it before it came out. So what we did is we took the ecFLEX, we applied a potential using ecFLEX of 660 millivolts versus a 100 ohm resistor and an 820 ohm resistor, and the currents changed accordingly, so we knew it was working. So hopefully this person will get back in touch with us and we'll dig in a bit deeper as to what's actually going on here. But I think it is a way of saying that we do try to support people. I mean, at the beginning of this webinar, was trying to support somebody with a cable, and I can give you the unofficial advice, which is cut the cable and solder on your banana plugs. But that's me as a private individual. I can't, as a company, we cannot recommend it. We can recommend our services to do it. I'm more worried about, it's not so much damaging us, it's damaging your own potentiostat, which that I'm a little bit, unsure I can take responsibility for. Somebody else is trying to measure magnesium and calcium and wants some advice around how to do this. So we do have a calcium sensor. I'll put a link to it. We don't have a magnesium sensor. By the way, we're more than capable of doing a magnesium sensor, but we need to do these in projects. We call them proof of principle. So if you Google Zimmer & Peacock proof of principle, you find out the kind of project that we would do. But I would actually say get going with calcium before you do magnesium. It's probably worth saying that we do these workshops, and we do cover these ion selective electrodes in those workshops, so I would recommend it. I've got a few links here. I've linked on the original one to the calcium electrode. Now I'm linking to the electronics that I would recommend, but because of the academic background, I'm also linking to an Arduino setup. So I'm, at ZP, we try to be completely reasonable with people. We understand the financial situations, especially at university. So we've linked to an Arduino. We can't support the Arduino option. I have it on the website. It's been up there for about 5 years. Take a look at it. But it's not something I can support. But I would obviously, want to be supportive of you, and that's why I've put that. Obviously, I will. The two other links will take you to some ZP products, and of course, I would be happy to support you on those ZP products. Question number 7. This is probably the easiest one for us this week. Somebody wants some graphene electrodes for the detection of proteins. The reason I'm talking rather fast is, like I say, body clock's a little bit messed up this week, and I'm trying to do this before I get too groggy. But they want to use graphene electrodes. They want to detect proteins. They want to use cyclovoltammetry and differential pulse voltammetry. So the Anapot 4 earlier on that I was linking to is completely fine. The Anapot EIS is also completely fine. It's even better, but the Anapot, sorry, I said Anapot 4. The Anapot is fine. The Anapot EIS is also fine. They'll both do cyclovoltammetry and differential pulse voltammetry. I'll be frank with you. I think, frank is just a statement of truth. We have the world's best commercial graphene electrodes around, and when I say the best, I'm also taking into consideration actually the cost. Graphene electrodes commercially are really expensive. Now, from universities, they may seem cheap, but it's just because they're not accounting for the effort that goes into them. But we actually have quite a low-cost graphene electrode, so I've linked to that. And I also have quite a nice paper on the modification here of, it says carbon electrodes, but it works perfectly well with graphene electrodes. So have a look at this paper. I've probably forgotten to put the link underneath, but it's an IEEE, and I think it's pretty much free. I know it's a good paper because my name's on it and several of our guys are on it. And what you do is you take this graphene electrode that I linked to earlier on. You don't necessarily need graphene for this, by the way. You can also get away with our hyper-value carbon electrodes. Our hyper-value carbon electrodes, if you buy a sheet of 300 of those that are perforated, you'll find them at really low cost. But you asked for graphene, so I gave you a graphene link. But earlier on in the webinar, I've also linked to our carbon electrodes for an earlier question. But you take your graphene or your graphite or carbon electrode, and you use this pyrene NHS. The pyrene is like a very aromatic, and it just binds quite nicely to the surface, and the NHS group is very reactive, and then you can start putting your antibody on there because you want to do protein detection. And protein detection often means that there's some sort of antibody to the protein. So troponin I is a biomarker for cardiovascular disease. It's a protein. You use the antibody for that, but you haven't said what protein you're after, but this is really the strategy that I would use. Take the surface, be it graphene or be it graphite, bind to it with this pyrene NHS. You've now got a very reactive surface of NHS. You can add your antibody to it, That'll stick to the surface, and then you can block it with chitosan. I think it was chitosan that we used in the paper. You did say that you want to do cyclophotometry. We would also do cyclophotometry as well, because we do cyclophotometry when we make this electrodes, make sure everything's working okay. We'd use about 5 millimolar ferricyanide to do this work, in about 1 molar KCl, just to sort of get a nice voltammogram. It tells us that the surface is pristine. As soon as you start adding these extra layers on it, it will distort any cyclophotometry, which is good because it tells you that you are now modifying the surface. If it didn't change, then you're not modifying the surface. In this paper, we actually did test the surface using differential pulse voltammetry. We use a reporting molecule, which I'm trying to think, it's probably ferrocyanide. And as we bound to the surface, the signal by differential pulse voltammetry increased. In fact, we used ferricyanide because this looks like a reduction. So we go from ferricyanide to ferrocyanide. Very unusual that the signal increased with the binding of this protein in this case. The reason being is the reporting molecule, in this case, I believe it was ferricyanide, is negatively charged. And so it was probably being kept from the surface by electrostatic repulsion. But as this protein bound to it, it's probably neutralizing some sort of negative charge on the antibodies and actually allowing the ferricyanide to get to the surface. Now, that was the hypothesis, and the reviewers sort of agreed with it, but we didn't prove it. So, but in this case, the signal went up with binding, which was quite unusual because this is really a blocking assay, and you would have expected it to go down. But took the luck, and it essentially worked. So I would try this paper, follow this assay. It's quite simple, let's say, and the signal changed with concentration. And I'm sorry that I've spoken a little bit quick. Like I say, I've thrown the excuse out there at least twice now. Just a lot of travel, being at MIT all day, giving a presentation, being on the tour, early flights in the morning, and so just going through this rather quickly. But let me try and take my time on this. Right. So as a private individual, I recommend that you just cut the cable and put your banana plugs on it. As a company, we'd love to give you the wiring diagrams, but then that's going to suggest that we're condoning your homemade modification of the cable, and we have been burnt with this, people doing home modifications before. I actually understand you're a senior scientist and you could probably do this, so I wish you luck with it. That PEC2 cell inquiry, you seem to just have liquid on the outward port. I would just suck it out with a syringe, and then you'll probably be able to start adding material in the other side, and it'll work perfectly fine. If you get stuck, go to the vendor. This phenol sensor, the second paper, that was that Nature paper. The fact it's in Nature, it means a certain amount of quality, to be honest with you. So it's probably a paper that's worth looking. And then I think with that paper, they actually used a carbon electrode. So I've linked you to a carbon electrode that, the biggest user of ZP electrodes is ZP. Therefore, we really care about the quality of those electrodes. They're the best on the market. Why? Because we use them all the flipping time, and we need them to be good because I don't want to go in the lab and waste our time. So it's like, owning a restaurant, and we eat at the restaurant as well. Sarissa Biomedical, yep, those null electrodes that you were inquiring about, they do exist. And please come to a workshop that we're holding in September. And if anyone's out there looking to make modified electrodes, looking to design electrodes, we do have workshops around this. I hope it's useful to you. That ecFLEX, was tested by us using 660 millivolts, 100 kiloohms, and I think it was about 800 kiloohms. So we probably need to re-chat on this and find out what's going on. But I think for everyone else, it just suggests that we will be supportive as long as people are using our kit. With that calcium and magnesium sensor, I've linked to the calcium sensor. I've linked to electronics that we will support you upon. But I've also linked you to a free option, which is the Arduino. It's just I can't support you if you go down the Arduino route. Graphene electrodes, yes, we have graphene electrodes. They're pretty low cost and really high value and high quality. I've also linked you to a paper where you can use that pyrene NHS to modify, and then you can stick your antibody on there. Then you can put your chitosan on there, follow the paper, and it's at least a good starting point for you. Hope you use our Anapot or our Anapot EIS to do that work. That leaves me just to say thank you, and I'm sorry I've thrown out all these excuses for going rather quickly this evening, and I'm sorry that we've kind of gone several hours early on this video, but busy day tomorrow trying to catch flights and get on planes, etc. So I wish everyone we're close to the weekend, so have a happy weekend. There will be the vlog and podcast on Sunday, but otherwise, if I haven't completely answered all questions, I'm sure we'll pick them back up again in next week's webinar. But otherwise, I want to say thank you very much.